last class, we have completed a. So we have started work done for a constant force. We did last 3 numericals on this topic. The next is work done for a variable force. If you have a variable force, then how would you calculate work done? It's work done for variable force. So if you have a variable force, then you can't directly use that work done is dot product of force and displacement. For a variable force, the expression of work done is this. Work done is integral of f dot dx, and the limit is from x1 to x2. If you have a variable force, then you will first calculate work done for a small displacement, very small displacement dx. Then you will integrate it from the initial to the final position. So that's the entire expression of work done. It's integral from x1 to x2 f dot dx. So this is, we will use this expression if your particle is moving along x-axis. We use this expression for motion along x-axis. If motion is along y-axis, then you can use this expression. If body is moving along y-axis, then instead of dx, you can simply use dy. The limit of the integration is from y1 to y. This is motion along y-axis. Similarly, if a particle is moving along z-axis, if your particle is moving along z-axis, then you can write your work done as, this is limit z1 to z2, it's f dot dz. So this is if your particle is moving along z-axis. In general, if particle is moving in space, like x, y, z, all are changing. Then your work done is, it's integral f dot dr. The limit is from r1 to r2. So in general, this is the expression of work done from r1 to r2 f dot dr. So this is the expression of work done if your force is variable. Okay, just note it down. Then we'll do some numericals on this concept. So if you have a constant force, then you can do it directly, like fs cos theta is your work done. But if your force is variable, then you can't calculate it directly. You have to calculate work done for a small path, and then you will integrate it from initial to final. So you can write the expression of work done in this way. That work done is integral of f dot dx. The limit is from x1 to x2. Now, since your force F and displacement dx, force and dx both are acting in the same direction, so the angle between them must be 0 degree. So you can write this. Your work done is, it's x1 to x2. It's f dx cos 0. So x1 to x2, it's f dx cos 0. Cos 0 is 1. So this is integral x1 to x2, it's f dx. This is the expression of work done, x1 to x2, f dx. So this is the expression of force, it's 3x squared plus 2x. So work done is, just keep on substituting the limits. The limit is from 0 to 2. This is 3x squared plus 2x dx. You can divide this integral into two parts. So the work done would be simply, it's 0 to 2, 3x square dx plus 0 to 2, it's 2x dx. So you can divide it into two integrals. Now you can take this 3 as a constant, you can take this 3 outside, and this is 0 to 2. It's x square dx plus this 2 is again a constant, you can take this 2 outside. This is 0 to 2 x dx. So work done is 3. This is x square. So the integral of x square is it's x to the power 2 plus 1 divided by 2 plus 1. Limit is 0 to 2. So the expression of work done is 3. It's x cube over 3. Limit is from 0 to 2. Plus this is, there is 1, 2 there. So this is 2. It's x square over 2. Limit is 0 to 2. So this 3 will cancel this 3. This 2 will cancel this 2. The expression of work done is it's 2 cube minus 0 cube plus it's 2 square minus 0 square. So the expression of work done is it's 8 plus 4. So the work done is 12. So this is the total work done in this case. The total work done is 12 joule for an variable force. Okay, after this variable force, the next is graphical method to calculate work done. The next is the graphical method to calculate work done. So if you have force versus displacement graph, this is displacement S and this is force F. So you have this graph, force versus displacement graph. So the shape of the graph is something like this. This graph could be of any shape. If you want to calculate work done through this graph, then in this graph, work done is area under the graph. If you want to calculate work done, then work done is area under the graph. So this area under the graph is work done. So if you have force versus displacement graph, just calculate the area under the force versus displacement graph, and that area under FS graph will give you work. The work done is simply this area. There is one more convention that area above the displacement axis is considered as positive. Area below the displacement axis can be considered as negative. So remember this thing. Area above the displacement axis is positive and area below the displacement axis is negative. Area below the displacement axis is negative. So this is force versus displacement graph. If you have force versus displacement graph, then area above the displacement axis will be positive. Area below the displacement axis would be negative. And that is the total work, area under the graph. Okay, now solve this question. So you have this force versus displacement graph. This is force and this is displacement graph. The graph is like this. This is force versus displacement. This is 0. This is 2 meter. And this is 4 meter. This is 3. And this is -2. This is force in Newton. And this is displacement in meter. You're supposed to calculate work. So calculate work. Calculate work. Here work done is it's equal to area of rectangle plus area of triangle. So area of rectangle is base into height. It's 3 into 2. And the area, this is the area of rectangle. Area of triangle is half base into height. Half base is 2 into height is 2. But we will take this area as negative because this is below the time axis, below the displacement axis. So this is 6. It gets cancelled out, -2. So that is 4. So this is the work. That's area of rectangle minus area of triangle. That's work in force. The next is the mechanical energy. So in mechanics, a system can have two types of energies. Two types of mechanical energies exist. The one is due to the motion of body, which is known as kinetic energy. And another is due to the interaction, which is known as potential energy. So kinetic energy is due to motion of body and potential energy is due to interaction, due to forces. We will discuss potential energy later, but first let's complete with this kinetic energy. So these are two types of energies in mechanics. Body can have many types of energies like heat energy, sound energy, light energy. But in mechanics, we don't study heat energy, light energy, or sound energy. We just study two types of energies, kinetic or potential. And this kinetic and potential energies altogether are known as mechanical energy. So let's start with kinetic energy. Kinetic energy. So energy possessed by a body due to its motion is kinetic energy. So this is kinetic energy. Energy possessed by a body due to its motion is kinetic. So if you have a body and this body is at rest, so the velocity is 0, then it doesn't have kinetic energy, it's kinetic energy. But if this body starts moving with a velocity v, and due to its motion, this body will have some kinetic energy, and that kinetic energy is half mv square. So energy due to the motion of body is kinetic energy. Like if this pen is at rest, its kinetic energy is 0. If it starts moving with certain velocity, then due to its motion, it will gain some kinetic energy. So kinetic energy is half mv square. So kinetic energy is the energy possessed by a body due to its motion. That's kinetic energy. Okay, Fazil, does kinetic energy depends upon frame of reference or it is independent of frame of reference? Fazil. It should depend upon frame of reference or it should be independent of frame of reference?
Independent, sir.
Independent of frame of reference. When you're saying that kinetic energy is independent of frame of reference, that means you're saying, say, you have a car and it is at rest, This observer is in ground. He observed that car is moving with a velocity of 10 meter per second. So this observer and the mass of car is say m. So with respect to observer on ground, with respect to observer on ground, kinetic energy of car is half mass of car into velocity of car per square. So this is the kinetic energy of car with respect to an observer on the ground. Okay, if the same observer, this is car, it's moving with a velocity of 10 meter per second, mass of the car is m. If the observer is sitting inside the car, with respect to observer in the car, 10 meter per second is with respect to ground. If you are inside the car, then the velocity of car with respect to would be zero. Say, if you are on the ground, a cab is moving on the road, then you will observe the velocity of cab is say 10 meter per second. But if you sit in that particular cab, then with respect to you, that cab will come to rest. Once you are in the cab, you will observe that cab is at rest with respect to you. So if you are in the cab, then with respect to observer in the car, velocity of car is zero. This we did in relative velocity. Velocity of car is zero. If velocity of car is zero, Rania, what is kinetic energy of car with respect to an observer in car?
Half into m into 0.
Yeah, so it would be. So it will be zero. So kinetic energy is zero. So this car will have some kinetic energy with respect to an observer on the ground, and the kinetic energy of car is zero with respect to an observer who is sitting in the car. So the kinetic energy depends upon the frame of reference. Means it depends upon the place with respect to which you measure the velocity of car. If your observer is on the ground, then kinetic energy is non-zero. But if your observer is sitting in the car, then kinetic energy is zero. So kinetic energy depends on frame of reference. Depends on frame of reference. Frame of reference is simply place of observation. In this case, the frame of reference is ground. In the next case, the frame of reference is car. The next is derivation of the expression half mv square. To derive this expression, we will again use integration like so this is a body of mass m. I'm applying a force F over the body. Initially, the velocity of the body is zero. V1 is zero. Initial velocity of the body is zero. When you apply force, that means you are doing some work over the body. The body gets displaced by a certain amount due to force, and now the velocity of the body is v. So earlier, the kinetic energy of the body was zero. But due to this force and due to work done, this body has some non-zero kinetic energy. So supposed to calculate the kinetic energy. So to calculate kinetic energy, just calculate work done in carrying body from zero velocity to v velocity. If you could calculate work done in increasing the velocity of body from zero to v, then that work done gets stored in the body in the form of kinetic energy. If I consider this displacement dx, say, let's hold this. We are taking a very general case. If we consider that force is variable, so if I take a variable force, work done is integral of dot product of force and displacement. This is from 0 to, this is work. It's the dot product of force and displacement from 0 to V1. So this is 0 to V, and this is F dot dx. Now the next thing is you have to convert this dx into V, because the limit of integration is over velocity and this is displacement. So somehow you have to convert this displacement in terms of velocity. To convert this displacement in terms of velocity, we use some tricks. So I'm repeating it again. I'm considering that your force is variable. So work done is just integral of F dot dx. But instead of limit of position, you have limit of velocity. So you will convert this integral in terms of velocity, that means 0 to V. Initial velocity is 0, final velocity is 0. So you can write your force as the product of mass into acceleration. This is your force, the product of mass and acceleration. If I substitute the value of force here, this is 0 to V. It's mass into acceleration dot dx. So this is your force, it's mass into acceleration dot dx. In the next step, you can just write your acceleration as dv over dt. This is your acceleration, which is dv over dt. Instead of a, you can simply write dv over dt. And the expression of work done comes out to be, it's 0 to v m dv over dt dot dx. The next is, you can write this dx over dt, rate of change of position, dx over dt as velocity. This is velocity, rate of change of position. So instead of this dx over dt, I'm just writing v. So why I'm doing this? I'm just trying to convert the integral, which is in terms of dx, to an integral, which is in terms of velocity. Because the limits are in terms of velocity. You don't have limits in terms of displacement. That's why we are converting in terms of velocity. So if I substitute it here, it's 0 to v m dv dot v. 0 to v m dv dot v. Now dv and v both are acting in same direction, so the angle between them is 0 degree. I'm just opening the dot product. It's 0 to v. It's m. If I open the dot product of dv and v, this will be dv multiplied by v multiplied by cos 0. Cos 0 is 1. So this is your work done. It's 0 to v. It's mvd. This is the work. So you can further write this as that work done is m. It's 0 to v integral of v. See, you people never ask questions like why are you substituting a as dv over dt? Why are you writing v as dx over dt? Because when you do physics, these type of questions should arise in your mind. But why am I writing dv over dt? Why don't I just integrate f with respect to dx? Why I write this dx over dt as velocity? If you don't ask these type of questions to me or to yourself, there's no point in doing physics. Like physics is not just about memorizing formula and some derivations. It's quite more than that. Like, you can't really learn physics unless you ask these questions. Why is it doing? Why can't we do this in another way if you can think of some other method to do this thing? It's because the limits that you have are of velocity. You are integrating it from some initial to final limits. The limits that we have here are of velocity. That's the limits. Just due to the fact that these limits are of velocity. So work done is m, it's v to the power 1 dv. So if I integrate this v, this comes out to be it's v square by 2, limit is 0 to v. So work done is m by 2, it's v square minus 0 square. So if I solve this thing, this work done is half mv square. So this is the expression of work done. This work done gets stored in the system. Why you are doing this work done? You are doing this work done to increase the velocity from 0 to v. That's why you are doing the work done. And this work done gets stored in your body in the form of kinetic energy. This work done gets stored in the body in form of kinetic energy. So the expression of kinetic energy is half mv square. This is the expression of kinetic energy, which is half mv square. So this is kinetic energy. Yeah? Momentum P is equal to mv. So we can convert this expression of kinetic energy in terms of momentum. Like I can do this as half into mv square. I can do one thing, I just multiply numerator and denominator by m. So this comes out to be half m square v square over m. You can write this mv as p, so your kinetic energy is p square divided by 2. So this is the relation between kinetic energy and momentum. Kinetic energy in terms of velocity is half mv square. But in terms of momentum, this is p square by 2. This is the expression of kinetic. The next topic is work energy theorem. The next is work energy theorem. The derivation is same. Let's first we will do work energy theorem and then we will do numericals on this concept. So work energy theorem simply says if you do some work on the body, then due to that work done, the kinetic energy of body will change. This simple statement is work energy theorem. Whenever you do some work on the body, then due to that work done, kinetic energy of the body will change. This simple statement is known as work energy theorem. So work energy theorem simply says that change in kinetic energy of body is equal to work done. So work done is equal to change in kinetic energy. That is the work energy theorem. So work done is just final kinetic energy minus initial kinetic energy is work. This is the expression of work done. Final kinetic energy minus initial kinetic energy is work. Now to derive this work energy theorem, and when I say the work done, it's a total work done. If you have 4 forces in a system, then this work done is the total work done by all 4 forces. That's work energy theorem. So derive this work energy theorem, the same derivation, but instead of initially 0 velocity, let's say your body have initial velocity v1 and its final velocity is v2. Now, if you, and this is very natural, if you apply force on a body, then its velocity should change. If this pen is moving with certain velocity and apply a force over this pen, then its velocity will increase. So initially the velocity is v1, the final velocity is v2. I'm doing some work on the body. Is there any change in limit here? The method is same. We will calculate work done in changing the velocity, and that work done would be equal to change in kinetic energy. So there is just one simple change, and that change is in the limit. The entire calculation is same. The only difference is in the limit. Otherwise, everything is same. So the limit is from V1 to V2. 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 V1 to V2. It's V1 to V2. So this is V1 to V2. Limit is from V1 to V2. So this is V2 square minus V1 square. That's what. So this work done gets stored in the form of kinetic energy. So you can, or not as kinetic energy. The only difference is in the limit. That's it. So if I expand this expression, then the work done will be it's half m V2 square minus half m V1 square. That is the work. Final kinetic energy minus initial kinetic energy, that is the total work done. Half mv2 square minus half mv1 square. Or your work done is change in kinetic energy. This is work energy. Is it clear up to this point? It's just difference in limit substitution. Everything else is same. Okay, let's do some questions of work energy theorem. The first question is, this question is basically the relation between kinetic energy and momentum. Is momentum of body is increased by 10%. Calculate percentage change in kinetic energy. I'm giving you some hint that initial kinetic energy is P1 square by 2. This is initial kinetic energy, which is P1 square by 2. You can write your final kinetic energy as P2 square by 2. This is your final kinetic energy. You can write your P2 as P1 plus 10% of P1. This is final momentum. Final momentum P2 is P1 plus 10% of P1. Just substitute this value here and then calculate percentage change in kinetic energy, which is K2 minus K1 by initial multiplied by 100. Do these steps and calculate the percentage change in kinetic energy. See, the initial kinetic energy K1 is P1 square over 2m. Fatma 15, not 1500. So this is P1 square by 2m. Ke2 is it's P2 square by 2m. And it is given that momentum is being increased by 10%. So you can write that your P2 is it's P1 plus 10% of P1. So P2 is P1 plus it's 10 by 100 P1. So your P2 is it's P1 plus LCM is 100. So this is 100 P1 plus 10 P1, which is 110 P1 by 100. It gets cancelled out. It's P2, which is 1.1 P1. So this is final momentum, which is 1.1 times the initial momentum. That's P2. The final kinetic energy Ke2 will be 1.1 P1 square over 2m. So the final kinetic energy Ke2 is 1.21 T1 square over 2. So this is K1 and this is K2. So percentage change in kinetic energy is final minus initial kinetic energy divided by initial kinetic energy multiplied by 100. So the percentage change in KE is final is 1.21 T1 square by 2m minus T1 square by 2m divided by P1 square by 2m multiplied by 100. Now from numerator, you can take P1 square by 2m as common. This P1 square by 2m is common and you are left with 1.21 minus 1 over it's P1 square by 2m. This P1 square by 2m will cancel this Pm square by 2m. So it comes out to be 0.21 into 100, which is 21. So this is the percentage change in kinetic energy. There's one more question on the same work energy theorem, and that question says, okay. See, the mass of the bullet is 10 gram. So it's basically 10 into 10 raised to the power minus 3. It's 10 raised to the power minus 2 kg. This is the mass of the bullet. The initial velocity of the bullet is 800 meter per second. Rania, what answer are you getting? 100 meter per second. So the first part says change in kinetic energy. Change in kinetic energy is final kinetic energy minus initial kinetic energy. The final is half m v2 square minus half m v1 square. So you can take this half m as common. It's v2 square minus v1 square. So you can take this half m as common. How much is v2? v2 is 100. It's 100 square minus v1, which is 800. It's 800 square. So it's half. Your mass is 10 raised to the power minus 2. This is 1000 minus 800, 8864. So your change in kinetic energy comes out to be it's half into 10 raised to the power minus 2. This is 10,000 minus 6,40,000. So this is minus of 6,30,000. So this I 235000. So the change in kinetic energy comes out to be minus 32500 into 10 raised to the power minus 2. Change in kinetic energy comes out to be minus 325.
It's 3155.
3 Yes. Three one three one five 315. So that's minus of 315. Hmm. For the second part, work done by resistive force. So how do you calculate work done? Your work done is change in kinetic energy. So you can write that your work done is minus of 315. This is the work done. So work done is minus of 315. After work done, the third part, average resistive force offered by mode. For the resistive force, you can use that your work done is force into displacement. So this is the bullet. It enters with a velocity of 800 meter per second. And when it reaches here, its velocity is 100 meter per second. And the displacement that it covers, what is the thickness of the wall? What is the thickness of this mud wall? 1 meter. This is offering an average resistive force of F. So the work done here is, it's Fs cos theta. That's the work done. So you can substitute the values, the average. So work done we have already calculated in the last part. This is minus of 315. Your displacement is 1 meter. Angle between force and displacement is 180 degrees. The angle between force and displacement is 180 degrees. If I substitute all these values here, so this is the resistive force. If this bullet enters in the mud, then mud will offer a resistive force which will oppose the motion of the bullet. So I'm using the work done, which is Fs cos theta. This is work done by the resistive force. Your work done is minus 315 joule. Displacement is 1 meter. Theta is 180 degree. Get the value of F. So your work done is minus 315. Your force is unknown. Displacement is 1, and this is cos 180. So minus 315, cos 180 is minus 1, so minus F. So F comes out to be 315. Or my cos 180 is minus 1. Cos 180 is minus 1. That's why this is 315 meter. You can use this concept that work done is Fs cos 180, which is change in kinetic energy. Here final velocity is 0. It's just able to pierce, means when it comes out of the plank, its velocity comes out to be 0. Use this equation. So you have first plank, a piece of wood, bullet enters here with a velocity of 100 meter per second. The thickness of the plank is 4 centimeter. And when it comes out of, this is V1, it's just stop. V2 comes out to be 0. The average resistive force is F. Then you have another plank. So you can write this particular equation for this case. Then take another plank. Thickness of the plank is 9 centimeter. So the velocity v1 is 100 meter per second. When it just comes out of the plank, that v2 is 0, and this is the resistive force. Write this equation for both the cases and divide. Then you can calculate this. This v1 is unknown. Okay, I'm writing this equation for the first plank. Say force is F, displacement is 4 centimeter, 0.04 meter, cos 180 degrees minus 1 is equal to change in kinetic energy. Final kinetic energy is 0. Initial is 100 square. That's first equation. Then here, same force, but now it's covering a displacement of 0.09 meter. Cos 180, it's minus 1, is equal to half m. Final velocity is 0. Initial is v1 square. That is equation number 2. Just divide 1 into. Divide equation number 1 and 2 and get the value of v1. So if I divide these two terms now, then this is f into 0.04 with a negative sign is minus of half m into 100 square divided by, it's minus f into 0.09 9 centimeter thick, na? Half m v1 square. So this f will cancel this f, minus half m will cancel this minus half m, negative sign will cancel this negative sign. It's 4 by n, 9, which is 100 square divided by v1 square. So if you have v1 square, it's 9 by 4 multiplied by 100 square. So if I take root, then v1 will be 3 by 2 into 100. So your v1 will be 150 meter per second. So again, so that was the velocity.